Welcome to another video. This problem is from the 1961 International Mathematics Olympiad, and it was question number 1. At first glance, it looks easy, and I can tell you it is easy relative to the newer questions I see these days. So I decided to give it a shot, and you're gonna leave a comment in the comment section if there's anything I left out. But this is how I did it. Let's get into the video. So the mission for this video is to answer the question that says solve for x, y, and z. And we see that x plus y plus z equals a, x squared plus y squared plus z squared equals b squared, and xy equals z squared. So everything is in terms of a and b only. So when we get x or y or z, we're just going to get it in terms of a and b. But there's a second part, which was the part that was very technical and hard to show, is to find the conditions that must be satisfied by a and b so that the answers we get, x, y, and z, will be distinct positive numbers. So it means x will not be equal to y and y will not be equal to z, and they have to be positive numbers. So this is a premise we're going to use for whatever we're doing. Okay, let's begin. As a habit, every time I see an expression like this, x, y, z, and then I see x squared, y squared, z squared, the first thing I do is to square this and see what shows up along with this, and I know it. So whenever you square something like this, this is what you get. You get a squared, not a, you get x squared plus y squared plus z squared plus 2 times xy plus xz plus yz. Okay, space is tiny. This is the expansion. It's just very, I did this so you can get used to it in case you do things like this. Now from here, I know that x plus y plus z equals a, and I know that x squared plus y squared plus z squared equals b squared. I just need to find something for this. But if you go to the third part, it says xy equals z squared. So I'm going to go here and replace xy with z squared. Okay, now watch this. It means I can factor out z from all of them. So if I factor out z from everybody, what's going to happen is this is going to become x squared plus y squared plus z squared plus, if z comes out, it's going to be 2z. And inside, I'm going to have z plus x plus y, which is x plus y plus z. So as you can see, I have x plus y plus z squared will be this plus this. So I can put the numbers there. This is a squared equals this here is b squared. And this is plus 2z times, this is a right here. 2za or 2az. So from here I can isolate z and I can say that z will be equal to a squared minus b squared over 2a. Actually, I just found the first answer. So I just solved for z. That looks very easy, right? Let's go back here and see how to solve for x and for y. Let's go here. Let's do some work. Now look here. We see that xy equals z squared. And we know that x plus y is a minus z. And we also know that x plus y is a minus z. So all we have to do is solve this system of equations, maybe make one the subject of the formula, and then see what happens. Like from here, this implies that y equals z squared over x. Here, I am going to replace y with z squared over x. So I say that x plus z squared over x is equal to a minus z. I'm going to have x squared plus z squared equals a minus z, so that, I can actually form a quadratic from here. X squared, where is my x? Oh, a minus z times x. Come on. So I have x squared minus a minus z times x plus z squared is equal to 0. So if I use the quadratic formula, x is going to be minus b, but this is my b, so it's going to be minus a minus z. Plus or minus square root of b squared is going to be a minus z squared minus 4ac is going to be 4 times 1 times z squared, which is 4z squared all over 2. Okay, this is what I have. But remember, my answer cannot be in terms of z, it has to be in terms of a and b. So all I have to do now is replace, wow, that's going to be a lot of simplification. I have to replace z with the answer I got here. Okay, let's do it somewhere here. Equals a minus a squared minus b squared over 2a. Okay, if we simplify this, you multiply, well, if you multiply this by 2a, it's going to be 2a squared over 2a minus a squared minus b squared over 2a. Let me put this in parentheses so it helps. What do we have? Well, the denominators are the same. That's 2a, and the top is going to be 2a minus a squared. That 2a squared minus a squared is going to be a squared, and then this minus will change this into a plus. So this becomes a squared plus b squared. So this first term is actually a squared plus b squared over 2a. Okay, so that's the first part here, plus or minus the square root of the same thing, a squared plus b squared over 2a squared, minus 4 times z squared. What is z? This is z. Oh, okay, times 4 times this squared. That's going to be a squared, is it plus? Minus b squared over 2a, everything squared. Come on, that's a lot. Everything divided by 2. Interesting. All over 2. That's what this is. So remember the mission. X is supposed to be distinct, positive. I thought the word real was there. They don't need to say the word real. Remember, only real numbers are positive. Complex or imaginary numbers are neither positive nor negative. So that word real is not necessary when you see the word positive. You just got something. Now, in order for X to be real, whatever is here must be greater than 0 or equal to 0, but it cannot be negative. And this is where the work is, okay? In order for this to be real, we clearly can see that this is a positive expression. Well, there's so many things we're going to talk about after this, but let's simplify this first. Okay, I hope this is not too tiny for you to see. I need to focus on this because that's what determines whether we're going to get positive or negative or real or complex solutions. So if we focus on this middle part, what do we get? I'm just going to resolve it here. We know that if you square this, you're going to have a squared, a to the 4th, plus b to the 4th, plus 2a squared b squared. And everything here is going to be 4a squared. Now, don't forget that we can actually drop this, take the square root and drop it since it's common to both of them. But let me just leave it for now. And we're going to have minus, since the denominators are the same, we're going to have minus. If you square this, it's going to be 4 times. So minus 4 times, if you square this, it's going to be a to the 4th. That's done. You do the same thing, you square this is going to be positive, but with a minus, it's going to be minus 4b to the fourth. And then there's going to be a squared b squared, which is going to be twice, but it's going to be minus. So if you multiply by minus 4, it becomes plus 8a squared b squared, and everything the same as this one over 4a squared. Let's move this to the middle, 4a squared. So how does this simplify? This becomes a to the fourth minus this is going to be negative 3a to the fourth. And I'm going to have this minus this, going to be negative 3b to the fourth. And then I have 2 of this plus this is going to be plus 10a squared b squared, all over 4a squared. I want to see whether this is positive. Is there a way to factor this? It looks like this can be factored actually. Okay, look, we can write this as, so let's focus on the top, just the top part here. This can be written as, I'm going to take out the negative sign so it makes life easy for me. Negative, we have 3a to the fourth plus 3b to the fourth. Okay, because this is to the fourth and this is what's in the middle, I'm actually going to write this as 10a squared b squared in the middle. A squared b squared, and this is going to be minus now. Because I factored out a negative, this changes to a minus, and this is plus 3b to the fourth. Now, can this be factored? Yes. Multiply 3 by 3, what do you get? You're going to get 9. What two numbers will you multiply to get 9? For their sum is 10. Well, it's going to be 9 and their sum is minus 10. So it's minus 9 and minus 1. And if you factor this on that basis, what you're going to get is this is the same thing as, it's going to be 3a squared minus b squared times 3b squared minus a squared over 4a squared. That is the factored form of this. Now, this is where the thinking begins. I did some surgical cleaning. Now, when you factor this, this is what you get. Remember, we want to know when this is going to be positive, because if it's not positive, this condition that we're looking for, what conditions must A and B satisfy, will not work, because we're not going to get positive numbers because they will not be real. Okay, so I said we're going back to the beginning. Look at the very first condition. If x, y, and z are positive, then A must be positive. Okay, so we know that A is greater than 0 from the very first condition. The problem we're having is we don't know whether B is positive or not because it is squared. Okay, so but if we can find a relationship or a connection between A and B, then we can come to a conclusion. So on this basis, is there a way we can find a connection? Yes, we know that A is positive, and we also know that Z has to be positive. So what must happen between A squared and B squared? Well, the top has to be positive. If the bottom we know is positive, and this is positive, then it means A squared is greater than B squared. That's the only way you can have a positive number, not 0. Okay? Remember, it's positive, not 0. So it means from here, this implies that A squared is greater than B squared because Z is positive. And what does this mean? If you take the square root of both sides, the absolute value of A must be greater than the absolute value of B. But we know A is positive, so we don't need the absolute value sign. We just need to say that A is greater than the absolute value of B. So this is a second condition. This is one, this is another one. A is positive and A is greater than the absolute value of B. But that's still not sufficient for us here. If X has to be, remember, the mission is to make sure X is positive. Okay, we're going to come back to distinct. Let's talk about positive first. Now, if X has to be a positive number, it means it has to first be a real number. For this to be a real number, this multiplication has to be positive, We already know that 4a squared is positive. So if the top is positive, both of them have to be positive or both of them have to be negative. So that's what we're going to investigate now. So suppose both of them are positive. Let's assume that both of them are positive. Then it means that 3a squared must be greater than b squared. That's obvious. We already said that a is greater than b, the absolute, so their squares are greater. So if you now multiply this by 3, it will definitely be greater than b squared. So this one checks out. But that means this two must be positive, okay? So if this is positive, it means if 3b squared minus a squared is greater than 0, it means that 3b squared is greater than a squared, which means that if you take the square root of both sides, the square root of 3 times the absolute value of b is greater than a. The absolute value of b is less than a, and a is less than square root of 3 times the absolute value of b. This is another condition. So we've got three things we're looking for. We know that for this to be true, this has to be true, this has to be true. And this is the value of z, and this is the value of x, and the value of y is just z squared divided by x. Just write it like that. You already found it. Okay, now, because I'm not going to write that, I don't even have space for it on the board. I did some cleanup, and now I have represented what we have here. Z is this, and x is this, and we have these conditions. Now, there's one more thing I haven't computed, y, but I need to be able to show that y has to be positive. Well, if z is positive and x is positive, once x is positive, y has to be positive by reason of this relationship. So we know that since x is greater than 0, y is greater than 0, because x, y is greater than 0. Okay, so that's it. Once both of them are greater than 0, once one is greater than 0, the other has to be greater than 0 because their product is greater than 0. It is a square. Now that's done. One more thing to do, show that they are distinct. That is, they are not equal to, no two of them is equal to the other. Now, this is going to be by contradiction. That's what I'm going to do. Okay, want to show x, y, z are distinct. Okay, now suppose x is equal to y. Let's assume you just have x equal to y. Well, there's going to be a problem here. xy will be equal to x squared, which will be equal to z squared, which means x is equal to z, because they're both positive, so I don't need the absolute value sign. So that means x equals y equals z. There's going to be a problem. And the problem is that if you go back to the beginning, which implies x plus y plus z will be equal to 3z. That means 3z is equal to a. Because x plus y plus z is equal to a, and that means 3z equals a, which means z equals, this implies z will be equal to a over 3. But if z equals a over 3, it means a over 3 is equal to this. You see that? Okay. This implies a squared minus b squared over 2a is equal to a over 3. If I multiply everything around, see what you're going to get. That is, we have 3a squared minus 3b squared is equal to 2a squared. which means if I bring 2a squared here, I have a squared minus 3b squared is equal to 0. Can you already see there's a problem? Which means that a squared is equal to 3b squared. Which means that a is equal to the square root, the absolute value of b. But we already said this cannot happen. So, because of this condition, a is less than the square root of 3, rad 3 times the absolute value of b, this condition contradicts this original condition on the basis that they are all positive and they are equal, so it doesn't make any sense. So this is a contradiction. So, therefore, x is not equal to y, and it's not equal to z. I think I'm done here. Never stop learning. Those who stop learning, stop living. Bye-bye.